Let's see. So we were around here. We were talking about the convection cycle. So convection again is the movement of hot air. Okay. Uh, Remember the idea of a parcel is just a like imagine a balloon filled with air, but there's no actual balloon there, right? It's just a portion of the air. So a parcel will rise, of course, and a cool parcel will sink. So that right there is a convection, right? The warm air is rising, it cools. As it gets higher and higher in the atmosphere, you get lower density, and so that cooler air will sink. Um, so warm air is less dense than cool air. So convection current stirs the wind. So wind is the air that flows horizontally. Okay, so that's important. These convection cycles that we're talking about are, um, there is some component that is horizontal, but for the most part, you're thinking about the air rising and falling, rising and falling. All right, and the part that is horizontal is really what we consider the wind. So the wind is the air that flows horizontally from high pressure to low pressure. It always goes from high pressure to low pressure. So the greater the pressure gradient, the gradient, of course, is the difference in the pressure, the stronger the wind. All right. So pressure differences are caused by uneven heating of the Earth's surfaces. The Earth's surface. Local differences in the heat contribute to small-scale local winds. Um, Planet scale differences occur because of the solar intensity variations. You get more intensity at the equator, then less intensity at the poles, and of course it varies according to the time of year as well. But right now we're just talking about the overall planet scale temperature difference. On any given day, there's a difference between the pole and the equator, there would just be a norm, just as there would, you would think, okay, well, there must be this huge convection between the equator, so the hot air rising from the equator and then falling near the poles, and that again, I think I mentioned this earlier, and that would absolutely be true. There would just be this one convection in the northern hemisphere and one convection in the southern hemisphere, but that's not the case because our Earth is spinning, and that spin causes what's called a Coriolis force. All right, so we'll get into the Coriolis force in just a moment. So the differences contribute to the global wind patterns, the thing called the prevailing winds. We're going to talk about that as well. All right. So the atmospheric pressure is greatest near the Earth's surface. Why? Why is that? Because of the weight of all the air above. That sounds like the right answer to me. Let's continue. 90% of the Earth's atmosphere is in the troposphere. That's true. Let's see. Atmospheric pressure is greatest near that's not exactly the answer for B. B is it's kind of true, but that's not really the reason. All right, C. Let's see. Because of warmer temperatures. What the heck does that mean? Let's see. So the atmospheric pressure is greater because of warmer temperatures? No. And because of water vapor? No, that's definitely. So I would say A is the right answer. And there it is. All right. And then what drives air from areas of high pressure to low pressure? That's the gradient, right? The difference in pressure. There's always got to be a difference in pressure for the air to move. All right, so the pressure gradient. What are these other answers? So because of convection, because of the wind. I mean, water vapor. You have to have that pressure gradient to get the wind and to get the convection currents. All right, so let's see. warm air is characterized. Warm air expands. Warm air has lower density, so you got to keep that in mind, right? Lower density and therefore lower pressure, right? Because remember, what's going on with the air is you imagine a parcel of air, so some volume of air, and what's happening when it's warmer, that those air molecules spread out more, right? And that spreading out is lower density, and because it's lower density, it is also lower pressure. And so remember, the air always goes from high pressure to low pressure. So, and then of course, cooler air characteristics. The cool air contracts. All right. So if you imagine a parcel of air, it's colder. Let's see. So here's a good example of this. Like if you take a piece of metal, for example, and they do this with bridges, by the way. So like a hot piece of metal will expand, and a cooler piece of metal will contract. It'll get smaller. And that's exactly what they're talking about with the air. So imagine a parcel of air. It gets colder, and therefore the air molecules can get closer together than when they're warm, right? So cool air has a higher density, right? Because the air molecules can physically get closer together. Higher density means higher pressure, right? And remember, the pressure gradient always goes. The wind will go from high pressure to low pressure. All right, so local wind. Not all surfaces are heated equally. The land. So this is a great example, right? Land is the land will heat up a lot faster than water. So if you're standing near the shoreline, and this is here's a really good example. If you're, let's say you're at the beach, and you're right on the shoreline, you might have noticed this before. Almost always, right at the shoreline, there's almost always a breeze. It might be a slight breeze, but there's almost always a breeze. And like, when my kids were younger, we would, be standing near the shoreline, and that's where you'd fly kites. You always see people flying well, not always, but often you'll see people flying kites right at the shoreline, and that's because the same amount of heat is coming to the ground, to the land, and also to the water, but the water has a higher heat capacity, and so it takes the water longer to heat up, and it also takes the water longer to cool down. And so because the land heats up first, there's a difference there's a difference in pressure, right? And so remember for warm, the pressure over the land is lower than the pressure over the ocean, on the same day, let's say, right? And so that difference in pressure, it's going to cause a local some local wind, right? And that's what kids take advantage of that when they go out and fly a kite right near the shore. All right. So unequal heating results in pressure difference, and the pressure difference results in wind. Wind is air that flows horizontally, and it always goes from high pressure to low pressure. Okay, so keep that in mind. High pressure to low pressure. High pressure when the air is cooler. Low pressure when the air is warmer, right? Because warmer, it's spread out more. Cooler, it can contract. It can get closer. The air molecules can get closer. And so therefore that's higher pressure. All right, very nice. So here, let's see. More energy is required to raise the temperature of water than land. Once heated, the water retains the heat longer than the air, longer than the land. This is related to, well, we just talked about it. That's the specific heat, the high specific heat of water. Water has a much higher specific heat than land. And if there's an experiment, if you haven't done it yet, where you shine a light on some sand and some soil and some rocks and some water, and of course it takes a lot longer for the water to warm up, and so the water, it takes the temperature change in the water is much less than the temperature change in the rocks, for example. All right, so C is the right answer. Water has the higher specific heat capacity. All right, so and what's nice about that, the nice thing about that is once the water is warm, it will hold on to that heat, and that's kind of what the Gulf Stream does, right? The Gulf Stream, close to the equator is where it starts, and then it will head up the eastern coast of the United States, or right off the eastern coast, about 200 miles or so, and then it'll cross the Atlantic and heat up Great Britain and Norway and other parts of Europe as well. All right, so here's another one. A hypothetical schoolyard. There's this blacktop area and a grassy area. On a particularly warm day, a small breeze develops. The air moves from. All right, so let's be careful when you think about this. Okay, so does it move from the grassy area to the blacktop? From the blacktop to the grassy area? It never moves from low pressure to high pressure. It always goes. So let's think about it. So the blacktop is going to be the higher temperature. Right, so we'll go back here, and let's go back to this one right here. So higher temperature means lower pressure, right? Lower density, of course, and lower pressure. So keep that in mind. The blacktop has lower pressure. So the blacktop has lower pressure, and the grassy area will have it'll be cooler over the grassy area. But that means it'll have higher pressure than the area right above the blacktop. All right, and so the air will move from the grassy area to the blacktop. All right, so all right. Hopefully, make sure you rewind that and understand what the reasoning for that. Right, the air above is hotter. And so that is a greater the air above the blacktop is hotter, so that is a lower pressure. The air above the grassy area is cooler, so that is a higher pressure. So and the air moves from higher to lower, so it'll move from the grassy area towards the blacktop. All right, very nice. So this is the thing I was getting at before. So the Earth rotates, and it, by the way, we're rotating from east towards west. All right, so we're rotating. Hold on, let me think. Let me make sure I got that right. Hold on. West towards east, and another way of saying that, of course, is we are rotating counterclockwise. So if you were standing above the North Pole, the Earth would be spinning on its axis in a counterclockwise manner. Okay, so remember, all right. So with that in mind, the air gets deflected. In the northern hemisphere, it'll always get deflected to the right. In the